Hello everyone, we're going to be talking about the Euler-Lagrange equations, where as you can see here, where Euler-Lagrange equations is where the derivative with respect to time of the partial derivative of the Lagrangian with respect to a the derivative of a measurement is equal to the partial derivative of the Lagrangian with respect to said measurements. Here I can see v, which is position and displacement, and v for velocity, but you could just replace them with q at x and q dot at v to represent derivatives, and you can see it produces L equal to t minus v. Some of you may be asked at engineering courses to derive said thing, so we can use the action functional of s, where the coordinates of a, b, and the x and x positions all are in a manifold R. They are all in a real plane, and in order to find the pathway, you can find the s of q from a to b, of L of t, q of t, and q dot t with respect to t here. A path such as q in the set of P would be a stationary point if and only if we've got a function of the partial derivative of L for any order of Q dot I, where I is from 1 to any n, and that L is the function of the t, q of t, and q dot t. Take that function altogether, minus it by the derivative, and it should be 0, and that's where it should have a stationary point. So that'll become very, very, very fundamental. So a few definitions we may need to understand. XL is what I've outlined here as a real dynamical system. A real dynamical system is where we have a function phi where the potential U is in a subset of T product X, which goes to X, and the projection map of the potential is in the second projection map of U goes to X. X is also the configuration space, where L is, as already you can tell, L parameterizes T, Q of T, and V of T, and X is a smooth manifold, meaning that let's assume for any alpha from alpha subbase 1 to alpha subbase n in the set of natural numbers from 0 to n, and we've got U in the set of Rn tuple and V in the set of Rm tuple, the function of X being a smooth manifold is only smooth from U to V if the partial derivative of any alpha x for any is equal to partial derivative of any x, and for every capital X over lowercase x for any position and stuff, where that derivative, partial derivative, always exists. So we're doing a one-dimensional derivation because it seems to me it'll be very difficult to find another derivation for other dimensions. So we can already see we've already got the action function of the integral, and we've got to see here if f extremizes, any slight perturbation of f increases j if f is a minimum, and vice versa. Therefore, f plus epsilon eta is a result of the perturbation of epsilon times eta of f, where first of all epsilon is small, and eta is a function where eta at the endpoints of a and b, start and end, is equal to 0. So we can find the phi function. Here. Phi function here, and we can see how it links into the integral. So due to the parametrization, we would have to expand the derivative, and we can expand the derivative as well, and the function is already defined here as well. So we need to find the total derivative, and let's find the total derivative here of the function anyways, and as a result, by integration by parts, we can say that derivative is the integral of a to b of a to x, or the partial derivative with respect to f of x and epsilon a to x plus a to x, and the derivative with respect to x plus eta plus epsilon times the eta derivative of x, plus, as you can see here, the eta derivative of x of partial derivative of L with respect to f derivative of x, f of x, and that's the same thing as before. So you've got to understand, at epsilon equals 0, the whole derivative equals 0. So in here, as a result, this function, as I already stated, this function at the top here already parametricizes to 0, right? And as a result of it being 0, we can factorize the a to x from the first part and then leave the second. And we already know that the second part is already going to be equal to 0 because at the endpoints a to a and a to b are already equal to 0 right here. So as a result, we can just really leave with the first part of the equation, as you can see right here, where a to x is h of x and f of x is this whole function here, and that is equal to 0. And as a result, this is also equal to 0 because of the fact that if a continuous function at an open interval ab satisfies the equality of the integral of a to b of f of x h of x with respect to x is 0 for all compactly supported smooth functions on a to b, then f of x is equal to 0. As you can see here, the h of x is the a to x, because an a to x acts as the compactly supported smooth function. And as a result of that, this is equal to 0. And therefore, we can derive clearly the Euler-Lagrange equations. So, thank you for listening to my talk about Euler-Lagrange equation derivations. I hope this becomes really useful in your engineering courses. Sorry for the video quality. My camera is just not really doing well. So, thanks for viewing, guys.